Okay, we are starting chapter 3 with talking about exponential functions and what their graphs look like. So an exponential function has a constant as a base raised to the x exponent. So starting with how our calculators can evaluate this, if I have 2 to the x for my function, the caret button is where I make the exponent. So 2 to the x, when I plug in negative 3.1, 2 to the negative 3.1 is approximately 0.116629. We'll go to 4 decimal places. Okay, and then 2 to the negative x, so this will be 2 to the negative pi. And since it gave me the pi symbol and not 3.14, please use the pi symbol. Okay, 2 to the negative pi is approximately 0.1133. And 6/10 to the x, where x is 3/2. I'll type in 1.5. 6/10 raised to the 3/2 is approximately 0.4648 when rounded. Okay, so now what about graphs? In the same coordinate plane, sketch the graph of each exponential function by hand. So I'm going to make a table of values, and we'll do, let's call, so we have y, and then we have g of x. And when I pick points, I'm going to pick the basic -2 to +2. So that gives me 5 points and a pretty good shape of a curve. Okay. So if I plug in -2, I'm just going to do these in my head because this is not too bad. 2 to the -2 is the same thing as 1 over 2 to the second, which is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. So in blue, we'll do 2 to the x over here. 1/4, 1/2, 1, 2, 4. So we do have to be careful about how we curve this. This should approach the x-axis to the left, but never cross it. And then it does go up pretty quickly as we go to the right. Now 4 to the x. So 4 to the -2, again, that's the same thing as 1 over 4 to the second, which is 1 over 16. 4 to the -1st is 1 over 4. 4 to the 0 is 1, 4 to the first is 4, and 4 to the second is 16. So sometimes they are going to exponentiate so quickly that we're not going to be able to graph that. Like 216 is not on this graph, but that's okay. We're just going to graph whatever we can. So 1/16 is here. 1/4 is about here. 1, 4, and make sure that it goes up quick enough that it could get to 16 at 2. There we go. Okay. So as we can see, the bigger the base number, the faster it increases as we go to the right. What if we have negative exponents? So same deal, we are graphing 2 to the negative x and 4 to the negative x and see what those look like as opposed to the positive exponent versions. I'm going to plug in the same points. -2, -1, 0, 1, and 2. So this time when I do 2 to the negative x, it actually becomes 2 to the x if I'm plugging in a negative number. So 2 to the negative second would be 4. 2 to the first then would be 2. 2 to the 0 is 1. 2 to the -1 is 1/2, and 2 to the negative second is 1/4. So this is actually inverted of what we did up above. And make sure it does not cross the x-axis, whoops, like that, as we go to the right. Let's just be as careful as we can to not cross it. There we go. And then with the green, that's going to be 4 to the negative x. So same deal, when we do 4 to the negative 2, it becomes 4 to the 2, which is 16. 4 to the first is 4. And then again, this is just inverted from what we had up above. And I plot those points. There we go. Okay, so let's talk about what these basic graphs are doing. If we have a graph of a to the x, where a is bigger than 1, our domain is infinite, all real numbers, as we saw from those graphs, and our range is positive. It's from 0 to infinity, but it never touches the x-axis. And then that would be increasing. So we saw that they both all went through 0, 1. So there's a basic graph of an exponential growth function with a being bigger than 1. And if a is less than 1, so we haven't seen that, but we did see where the exponent was negative, and it's going to look very similar. Having a fraction or a number less than 1 as your base is going to turn this into exponential decay. Oop, don't want to miss. Still going through 0, 1. But we have decay, and it still has all real numbers for the domain with the range from 0 to infinity. So now in terms of transformations and what these graphs would look like, we got to think way back to chapter 1 where we had graph transformations and talking about reflections and horizontal vertical shifts. So because that on letter A, that +1 is in the exponent, that's the same thing as being inside the function, so that will be a horizontal shift. And the horizontal is always opposite what we think it's going to be, so this would be left 1 in comparison to f of x. So now if I have a movement on the outside, so 3 to the x minus 2, that would be a vertical shift, and the negative 2 is going to move it down that many units. And then looking at C and D, the difference here is where the negative is. If the negative is out front, that is an x-axis reflection. Reflection over x-axis. And if the negative is inside the exponent, so that is going to be a y-axis reflection, which is what we saw, which is why it turned into exponential decay instead of exponential growth when it was reflected with that negative. Okay, so there is a special exponential, and that is with a base e. So it's still going to look the same. We're still going to have that same basic increase, but e to the x is just a special exponential that we have talked about. And this example shows you why it's so special. But we are actually just going to move on to using it, using e to the x. So there is on our calculator an e to the x function. So the second natural log button here, so second ln does e to that. It gives us an exponent spot. So first let's type in e to the negative second, and what that looks like. 0.1353. E to the negative second, 0.1353. And then we have e to the 0.25. 1.2840, and e to the negative 4/10 is about 0.6703. Okay, so sketch the graph. So we are just going to make a table of values since I don't have a graph here visible, but we are just going to use our calculator to generate that table of values. If I go to y equals and type in that exact function that I see, 2e to the 2400ths x, and then I go into my table, so the values that I always use are from -2 to 2. So if I make this table, and you remember when you're writing down these values like you're going to sketch them on a graph, you don't have to go to too many decimal places because 1.23 is not going to look very different from 1.24 when you're approximating it on a graph. So I'm just going to go to 2 decimal places to everything since we can't squeeze that many decimals on this table. And we would sketch that if we were given a graph. If you want to look at what that looks like the exponential graph we've been dealing with so far where that it crosses at 0, 2. And it does that because of the 2 in front. That's going to be like a vertical stretch, is that it's going to become that much taller by a factor of 2. Okay, so next one we have 1/2 e to the -5800ths x. And we just want the table for now, second graph, to give us the table. From -2 to 2. And at -2, about 1.6. -1 is about 0.89. 0, 1/2, 0.5. 1.28, and 2.16. Now notice because of this negative up in the exponent spot, that's why this has turned into exponential decay. That's why the numbers are getting smaller. All right, let's look at these compound interest equations. Let me fix it before we talk about them. So that should be A equals PERT, where A is the balance in the account with P is the principal amount. After T years, the interest rate is R in a decimal form, so 5% would turn into 0.05. And N is the number of times compounded per year. So that's only relevant to number 1, which is compound interest, and 2 is continuously compounded interest. Okay, so let's do a couple examples with those interest equations. If we invest $9,000, okay, that's our principal, at an annual interest rate of 2.5%, so as a decimal, that's 0.025, compounded annually, so that's N, after 5 years, so that's T. So this is going to be the compounded N times per year equation. That would be number 1 on the last page. The 9,000 is in front. 1 plus R over N to the NT. Oops, that's a 5. And I can just type that into my calculator very carefully. Let me show you where those uh, parentheses should go. 9,000, too many. 1 plus 0.025 divided by 1 raised to the, and parentheses 1 times 5. 10,182.67 after 5 years. All right, now we have 2 different parts of this question. Both of them are $12,000 invested, so that's our P either way. Annual interest rate's 3%. T is 4. On letter A, we're compounding quarterly, so that's our N is, whoops, quarterly would be 4. So we do the 12,000 out front using the same formula we did up above, 0.03 divided by N to the NT. 12,000. 1 plus 0.03 divided by 4. Raised to the in parentheses 4 times 4, or you could have just put 16 right away. $13,523.91. We should always round to 2 decimal places since we're dealing with money. And last one is compounding continuously, so that is PERT we have to use. A equals P e to the RT. So that is how that question is a little different. When we're compounding continuously, we always use PERT. 0.03 times 4. 13,529 and 96 cents. So obviously compounding continuously is the best you can do, and no bank will do it for you because it's the best you can do. And down here are the homework questions for section 3.1 on exponential growth.